Hello students, welcome back. Now let's go to section 3, Binomial Distribution. This topic is a continuation from an earn model of lesson 3, an earn model with replacement. It's with replacements, so this is an independent repetition of the same thing over and over again. Okay, let's go. Let's begin. And first, we consider the simplest possible case, the Bernoulli random variable. Let's consider only two possible outcomes, 0 for failure, 1 for success, and nothing else. Here I'm using a color coding of 1 for success, blue, and 0 for failure, red, and no other color. Each outcome will have probability, so let P be the probability for success. Then, by default, the failure probability will be its complement, 1 minus P. Here's a summary version. The random variable x can take either 1 or 0, and the probabilities for those are P or 1 minus P respectively, otherwise impossible. This kind of random variable is called Bernoulli random variable. It's important that we have to have 0, 1, not 1 and -1, or 0 and square root of 17. It has to be 0, 1, nothing else. In this case, it's possible to prove that the expected value is P and the standard deviation is square root of P 1 minus P. Now, if you're not interested in the proof, just fast forward a little bit. If you are, then stay here and let's go through the proof. It's not too difficult. Let's calculate the expected value. What is the expected value? First outcome times first probability plus second outcome times second probability, third outcome times third probability, and so on, right? But then again, in this particular case, there is no third possibilities. You see, we have just 1, 0, nothing else. So we don't have to consider the third outcome. And the outcomes for first and second are 1 for success and 0 for failure. And the probabilities are P for success and 1 minus P for failure. All right? And what is this quantity? It's easy, it's P. So the expected value is P, and here's the computation with appropriate color coding. All right, how about the standard deviation? For that, let's find out the variance. And the variance by definition is this, x minus mu squared. So this expected value computation. So it's the same computation as before in terms of the probabilities, P versus 1 minus P. P versus 1 minus P. But not just x, but x minus mu squared. See, x minus mu squared here, and x minus mu squared there, where x value is 1 for success, 0 for failure, right? So 1 for success, 0 for failure. Why did I lose the color coding? So this computation will give me the variance. Does it make sense? Probability P versus 1 minus P. And then the outcomes are x minus mu squared, deviation squared, deviation squared. And x values are 1 and 0 respectively, so 1 minus mu squared versus 0 minus mu squared. By the way, what is mu? Mu is P, isn't it? So if you plug in mu is P, then you get the second line. And from there, you can do further manipulation, further simplification, and take the GCF out. And this part becomes just 1, so that's what we get in the end. That's the variance. Taking the square root, you're going to get the standard deviation. That completes the proof. Alright, so much for Bernoulli random variable, and that was for only 2 possible outcomes, nothing else. 0 for failure, 1 for success, with probability p for success, 1 minus p for failure. Now, let's repeat Bernoulli random variable many times, and that's called binomial random variable. Remember, bi means 2, and only 2 possible outcomes, 0 versus 1, you see. That's where the term binomial is coming into play. And then I hope everybody recalls these. The probability mass function, precisely r successes. So n choose r, p to the r power 1 minus p to the n minus r power. And this is the CDF, cumulative distribution function. This is a probability mass function, and this is CDF, so it's cumulative. So you have to add up the probability masses up to that point. So that's why we have this summation here. This is CDF. You see, less than or equal, that's CDF. Now, if you're not interested in the proof, then you can fast forward a little bit. Otherwise, stay here and let's go through with a sketch of proof. So how do we prove that? Let's consider this kind of situation. R consecutive successes, and then n minus r failures in a row. So we get blue, 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 repeated r times, and then r, red, 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 like this. Okay? So all those blues repeated n times, repeated r times, so that's p to the r power, as highlighted in blue, and then all those red balls repeated n minus r times, so we have n minus r power. So there you go, that's the probability. P to the r power times 1 minus p to the n minus r power for a probability of a single sequence. Now, what if I have different sequences with the same outcome in the end? So r successes and n minus r failures, but in different order. Well, I claim it's going to be the same anyway, because the multiplication is commutative, as we can see in these kind of examples. You see, I'm multiplying p 3 times and n minus p twice, one way or the other, like this or like that. It doesn't matter. Ordering doesn't matter because the multiplication is commutative. So in the end, same probability all the way, and then we have to add up the same thing a number of times. So how many number of times? It turns out it's a combination n choose r. So there are n slots, and then select r slots for success, and the other n minus r will be automatically failures, and that's it. So you don't really have to worry about arranging any further, because 0 and 1s, those are indistinguishable by themselves. So simply select r spots for 1, and that's it. The others are automatically zeros. So we have combination n choose r, n factorial over r factorial over n minus r factorial times p to the r power, 1 minus p to the n minus r power. So there goes the proof for the probability mass function, and the CDF is just adding up those probability masses up to that point. Do we have an example here? Okay, here goes an example problem. An urn contains 5 red, 3 green, and 2 blue balls. Choose 20 balls with replacement. What is the probability that you get exactly 5 blue balls? Exactly 5 blue balls out of choosing 20, so it's going to be this one, isn't it? Probability mass function is going to be precisely 5 successes out of total 20 draws, and then 5 power, 20 minus 5 power, so this is going to be 15 power, and then P, what's the probability of success here? How many blue balls out of total? That's 2/10. And then the failure, 1 minus 2/10, so there you go. And then 20 minus 5, that's 15 power. And then of course, you're going to calculate this one as well. And then that computation is, what can I say? It's tedious, but here we go. So it's going to be 20 times 19 times 18 times 17 times 16. So largest 5 numbers or smallest 5 numbers. 5.3.2.1. This computation eventually, after all the simplification, will become an integer value. That's a combination. And then multiply these, run your calculator, you're going to get what you want. If you do it right, you're going to get this number. The detail is left to the students. And the computation is, it's extremely tedious if you use handheld calculator. So my suggestion is to use some further technology aid like Mathematica program like this. You can use Wolfram Alpha too if you want to. Anyway, here we go. Now, what if you have a cumulative distribution function? At most 5 instead of exactly 5. In that case, you have to do the same computation 6 times. R value 0, 1, 2, 3, 4, and 5, and then add them all up. Good luck. Oh boy. So, no blue, 1 blue, 2 blue, 3, all the way to 5 blue. Add them all up. Good luck. Now, let's consider some empirical example. Suppose that the approval rate of a current president is 39% and the disapproval rate is 57%. The result is based upon a poll result published by Gallup Institute on June 10, 2020. So this is coming from a real example, so it's really empirical. Now, suppose that you select 18 adults at random from the population, and what is the probability that at most a third of 18 selected people approves the president? So at most 1/3, so 0, 1, 2, 3, 4, 5, up to 6, right? At most 1/3. Less than 1/3, then you have to stop at 5. But at most 1/3, so it goes up to 6. And then run your binomial computation for each. It's a dreadful computation, but if you do it right, you're going to get something like this. Binomial H choose K, where K goes from 0 to 6. And there you go. And then how about more than half of 20 randomly selected people? More than half, so starting from 7, greater than 6, so 7 or larger. By the way, here, excuse me, there's subtle difference between one and the other. Here, this is about approving the president. Therefore, you're using the probability for approval, 39%. So 0.39, 1 minus 0.39, do you see that? The second problem is about disapproving. So you have to use 57%, not 39%, 57%. So we have 0.57 and 1 minus 57. So you don't use 39% and 57% at the same time. Binomial probability distribution considers only one probability and its complement. So 0.39, then you have 1 minus 0.39, and there's no room for 57%. Now for 0.57, you get that, and 1 minus that, and that's it. No room for 39%. Okay, all done except one final formula here. Means and standard deviations of binomial distribution. And what can I say? These are just formulas, and you'll simply have to memorize them. We cannot deduce those at this level because we'll have to use multivariable calculus here. So I'm not going to attempt proving any of these. I'll just leave those as just formulas. For binomial sum, it makes sense, n times p. So p is repeated n times. Imagine rolling a die 600 times. And how many aces do you get? Well, 1/6 of 600, so 100 times, kind of like that. As for standard deviation, it's going to be tougher, but it goes like this. In this example, for example, approval rate is 39%, all right? So expected value for approval, if you have 1,000 people, is going to be what? 39% of 1,000 is 390. Easy computation, right? Just multiply. So that's NP. And then this one, well, it resembles that standard deviation computation for Bernoulli distribution, you see, square root of p1 minus p, but it's repeated n times, so we have n there. But why do we have it here is a bit tricky, but it turns out this way. And the proof requires multivariable calculus, so I'm not going to go in there. Now that was for binomial sum. And finally, binomial mean. For binomial mean, from here, we divide by n. So from here, divide by n. So it's p. So mu is p. Same here, we divide by n. So we divide by n. And therefore, this is square root of p1 minus p over n. Because you see, this n was, no, let's write it like this. Let's keep this n. N p1 minus p, and then divide by n, but n was outside the square root. So bring it in, I have n squared. So after simplification, we get this expression as you see there. But of course, no student will go through this deviation, go through this derivation, because that derivation by itself is incomplete. And you'll have to go all the way back to multivariable calculus with multiple integrals and all those kind of things, which I'm not going to go through. Otherwise, you'll simply have to use the formula there. This final form, I don't like it very much, so let's just keep it this way. Square root of p1 minus p over n. Which one is more important? Binomial sum or binomial mean? The latter one is far, far, far more important for our purpose. Binomial sum is important to a certain degree for some classroom example problem, just like I demonstrated, rolling a die many, many times, those kind of things, and that's about it. In empirical problems, it's going to be all about binomial means. But in terms of theory, this is more important because we have to establish this, prove everything, and then divide by n, then you're going to get this. So you cannot really throw away this binomial sum, especially in upper level classes. At 3000 level, I'm very much tempted to remove this and then going over there. But, well, I decided to refrain from that temptation. So here we go. Binomial sum may show up a little bit. And if you're preparing for some standardized exam like text exam, do not disregard this part because sometimes people may write something. But it's far more important to get absolutely comfortable with the formulas for binomial means. Expected value is p, and more importantly, the probability standard deviation is square root of p1 minus p over n. This formula is very, very important. Okay, so much for section 3. Let's meet again in section 4 in a separate video.